Okay, so today we're going to be finishing up with our factors affecting pulmonary ventilation. So finishing up thinking about the air physically moving in and out. Then we're going to move on to talking about the diffusion of gases across the alveolar membranes. So when we left off, we were talking about pulmonary function tests. Here's where we were applying our understanding of compliance and resistance as far as our alveoli and our respiratory portion of the pulmonary system works. So we were looking at these two things we can measure: the forced vital capacity, which is just how much air can you expel after you have a patient take the deepest breath they can, versus our forced or expiratory volume, which is a percentage, saying how much of that air are you blowing out in 1 second. And when we look at these two numbers, we can tell the difference between restrictive pulmonary diseases and obstructive pulmonary diseases. Because a restrictive pulmonary disease is like the lungs are restricted in how far they can expand. So this is a problem with the compliance. So we see in restrictive pulmonary diseases that we never get the full amount of air in our lungs. So we have a low forced vital capacity. Whereas with an obstructive disease, obstructive means there's a problem with resistance. There's too much resistance. Our bronchioles are too small. So we could eventually get that same amount of air, but we get there slower. So in that first second, our FEV is going to be lower than 80%. And 80% is our normal comparison number. So sometimes we might see these graphs like this, but more commonly, instead of graphing the volume versus time, we're going to see the volume versus the flow rate. So this picture looks a little different, but it's expressing the same information. So we can see here in the obstructive disease, so that was the one where we have too much resistance, we're still getting to the same final volume. So this is telling us that we're still going to have that same FVC, that same forced vital capacity eventually. What we see that our biggest difference, the most noticeable difference where we see things happening is here and where this peak is. So this is saying something about that flow rate. So this is related to those FEVs. So we can see that we have a lowered flow rate for the restrictive disease and actually also for the obstructive disease. So the obstructive one actually gets lower here. So we would compare the same things basically. So first we're going to check, do we get to the same FVC? Check mark. Okay, if we get to the same FVC, that means it's not a restrictive disease. All right. Okay. If we look at the FEV and we see it's below 80%, then we need to check, are we going to have a lower volume, or are we just having a low flow and eventually getting up to that same number? So this last concept is going to be critical to understanding our gas exchange in the next packet. So this is the concept of alveolar ventilation and minute ventilation. These are two related but different concepts, two different measurements. So we're going to start with the minute ventilation. The minute ventilation is really just how much air is entering and also therefore leaving the respiratory system at any given minute. Okay. So all we're doing with the minute ventilation is counting up the amount of air getting into your lungs in a minute. So to do this, we're going to multiply our tidal volume. So we talked about the different lung volumes last time. The tidal volume was just that 500 milliliters with easy, normal breathing, right? So we're going to multiply our tidal volume, which is something around 500 milliliters, times our respiration rate. That's what RR is. Respiration rate. So this is going to be like our number of breaths per minute. The normal number is something around 12. Okay, so if I'm doing my math right, does that give me 6,000? Can someone check my mental math? Is that right? Okay, good. Okay, great. Okay, so that's a normal minute ventilation. However, when we're thinking about gas exchange, we don't want to use just the minute ventilation to figure out how much oxygen, for example, we're going to get into our cardiovascular system. Because we have to keep in mind that in the conducting zone, right, so not the alveoli, not the respiratory bronchioles, but like our trachea, our bronchi, the primary bronchi, the secondary bronchi, the tertiary bronchi, the bronchioles, all those earlier areas of our branches of the respiratory system in the lungs, they're not going to participate in gas exchange. So we consider the air in them dead air because it's in your lungs, but it's not going to have those gases crossing the alveolar method. So we have to account for that anatomical dead space is what we consider it when we're thinking about how much fresh air is really getting into the alveoli. So this is why our alveolar ventilation is going to be different than our minute ventilation. When we calculate the alveolar ventilation, we're going to be calculating how much of that air that we breathed in, that fresh air, how much of it is getting into the alveoli. So we have to account for the dead space, and it's about 150 milliliters. So in sort of picture version, what we have happening here is kind of showing you the cycle of air movement into an alveolus. So that's the yellow. We'll go through it in steps. So here we see in purple at the top, we have fresh air, and inside the alveoli, we have our old air. So anything that was in the alveolus, we had O2 going into the blood, and we had CO2 going into this air. So that's what I mean by old air. We've already had this process happen, right? So we took the oxygen out and we put carbon dioxide in. So as we move forward, we're going to breathe in and we're going to push some fresh air into the alveoli, right? So that's coming through nasal passageways, for example, if you're breathing through your nose, in through the conducting zone, and some of it is getting pushed down into the alveolus. But we have to remember that dead air was kind of at the bottom of this column. So first what happens is that old air gets pushed farther down into the alveolus, and then some fresh air gets pushed in on top. Here we have our gas exchange for this breath happening. So CO2 is moving in, oxygen is moving out. And we now see a color change. We basically took this whole chunk that had actually entered the alveolus. That's where our gas exchange was happening. So now we see that we're adding that into our old air column, right? So now we're calling all of that portion that has been in the alveolus as old air. We sucked the oxygen out. And then we complete this as we breathe out. We breathe out some of that old air and replace it with fresh air, but some of it is still kind of stuck in the system at the bottom of this column. So when we calculate our alveolar ventilation, we're going to basically be accounting for this, that some of that old air is staying in the system. Okay. How we do this is pretty simple, actually. So our alveolar ventilation, all we need to do to figure out how much fresh air got into the alveoli is first we calculate our minute ventilation. Okay, so that's the calculation we just did. All right, so our tidal volume 500 times our respiration rate of 12. We had our 6,000. And then we're going to subtract out our dead space volume, which is 150, times our respiration rate again, because basically we forced that dead air 12 times into the lungs, right? Because it was there in the conducting zone. So that, is that right? I think that's about right. Okay. So we can see that this number is going to give us less than the 6,000 now. So our actual amount of fresh air, sorry, doing this not on paper, is not my strong suit. I think that's right. Assuming I did that math right. That's about what our alveolar ventilation should be. So all we're doing is taking the amount of air we breathed in and subtracting out how much of that was dead air, which for every breath was 150 milliliters. So as we move into thinking about the diffusion and exchange of gases, we're first going to be talking about the amount of oxygen, the carbon dioxide in the air surrounding us. But then as we start to talk about what's happening in the alveoli, we're going to see these amounts are going to differ. And that's because of this mixing of air in the alveoli, that mixing of fresh air and dead air. So what we're going to be going through over the next couple of minutes, and this will probably last into next time actually, but what we're going to be talking about is the fact that oxygen is going to be moving into the capillaries around the lungs at the same rate as it's being consumed by cells. So here we see oxygen moving into our bloodstream. That oxygen is traveling to the heart and it's getting pumped around out to our tissue. So we can see we had 250 milliliters per minute of oxygen going into the blood, and it's replacing that 250 milliliters of oxygen that is being used by our tissue. And the reverse is happening for the CO2. So if we're producing 200 milliliters of CO2 per minute, we're going to be breathing off 200 milliliters of CO2 per minute. This is because we want to keep the carbon dioxide and the oxygen content of our blood in the arteries the same, so that our tissues are getting the same amount of oxygen and removing the same amount of waste product as we need. Okay, so when we look at our arterial blood levels of oxygen and carbon dioxide, they're going to stay pretty constant because we're just replacing what we've removed. So a number we might calculate, depending on what we're trying to look at. Sometimes we'll look at our respiratory quotient, and that is just the ratio of CO2 that's being produced versus the amount of oxygen that's being consumed. But we'll continue to talk about this graph in the future. We're going to go through all the steps of it and all the different amounts at each of these points. But this is just our broad overview. I'm pulling in oxygen, replacing the oxygen being used by the tissue, then eliminating all the carbon dioxide we produce. So when we're thinking about how gas moves across the respiratory membrane, we want to think about something called the partial pressure of the gas. And the partial pressure of the gas is not the same as the moles of gas, not the same as the exact amount of gas, but it is going to be something that we use to kind of measure the gases in our lungs, in the air, as well as in the blood. So we're going to think about the partial pressure of a gas, and we're also going to think about how soluble each of our gases is in liquids. So we're going to see that carbon dioxide and oxygen have different solubilities in water and therefore in blood, which is mostly water. And this is going to affect basically the amount of gas that is crossing from your alveolar air into your capillaries surrounding the lung. The other thing we want to just briefly review here, right? Want to remember this membrane, right? This membrane between the alveoli and the capillary surrounding is really thin, right? We just have that type 1 alveolar cell. We have our sandwiched together basement membrane, and then we have an endothelial cell. And the lungs in general are specialized to have lots and lots of surface area for this gas exchange to happen. Okay. So we saw this equation before. We still are not going to need to do any particularly specific math with this, but our ideal gas law does influence the gases that we're tracking and that we're thinking about transporting into our body. So the basic idea here, right, is that the pressure of a gas is dependent on the temperature, the amount of that gas. So N is like the moles of the gas, so the number of gas molecules, as well as the volume of the container we're in, right? So before we were looking at this equation to understand the fact that we have kind of an inverse relationship between pressure and volume, right? So that as we adjust volume, we adjust pressure. Here we're going to be thinking about it just to kind of understand why we might talk about the pressure of the gas, that the pressure of the gas is a sort of indirect measurement of the amount of gas, kind of. So when we think about partial pressures of gases, what we're really talking about is the fact that the air in your lungs or the air in our environment, right, it's a mix of gases. It's not pure oxygen, it's not pure carbon dioxide. It's a bunch of stuff mixed together. So when we measure the pressure of the atmosphere at 760 millimeters of mercury, right, that's not actually telling us about the amount of oxygen specifically. It's just telling us about the pressure of all the gases mixed together. So when we start to think about the respiratory system, we want to know specifically about oxygen. We're also going to want to know about carbon dioxide. So to calculate the partial pressure of a gas, all we need to do is to think about the total pressure of all our gases mixed together, which is what we would be able to measure, right? Like that 760 for the atmospheric pressure. That's what we measure. And then we just take the percentage of that air that is oxygen and multiply it by that number. So what we're saying here in this equation, right, is that our total pressure, so that like 760 is the pressure of our oxygen plus the pressure of nitrogen plus the pressure of CO2 and so on. So because of this, we can get a percentage for example, oxygen. And then once we have that percentage, we can move backwards and say, okay, so our percent of that gas that was O2 times that total pressure, which for the atmosphere is 760, is going to give us the partial pressure of the gas. Specifically in the air around us, most of the air is actually nitrogen, like 79% is nitrogen, 21% is oxygen, and a teeny tiny amount, 0.03% is carbon dioxide. So we have trace amounts of other gases, but they don't add all that much to our total pressure. So when we're doing this math, we're going to use these rough percentages, about 79% nitrogen, 21% oxygen. So to find the partial pressure of nitrogen, all we have to do is take that 79%, right? So we've converted it to a decimal here. So we took the 79% of nitrogen, and then we multiplied it by our atmospheric pressure. And that gives us our partial pressure of nitrogen, which is 600 millimeters of mercury. So this means we can do the same thing for any of our other gases, but the one we're paying attention to here is oxygen. Right? Oxygen is really important for our body. So we just take that 21%. We multiply it by 760, which is our atmospheric pressure. And this gives us a partial pressure of 160 millimeters of mercury. So these are going to be the partial pressures of nitrogen and oxygen in the atmosphere around us. But these are not going to be the partial pressures of oxygen and nitrogen in our lungs, because we're going to have that mixing of the dead air with the fresh air. The other thing that's going to make a difference, so remember, as air moves through the conducting zone, so as it moves into your lungs, we're warming it up and we're adding humidity, right? We're making that air warm and moist, so it plays well with the tissues in your alveoli. So as we humidify that air, we're also going to need to take into account the water vapor that is now composing part of that pressure inside your lungs. So the partial pressure of oxygen, or of water at 100% humidity is 47 millimeters of mercury. So this is now going to be changing the composition of the air moving into our lungs as we're warming it up. All right, so before, I'll highlight our differences. Right, before, our partial pressure of nitrogen was 600, but now we're down to 563 because some of that space in the air, some of that pressure is now taken up by our water vapor. And this means that our oxygen partial pressure has also gone down. So oxygen was at 160, I think. Now it's at 149. So this has gone down, again, because some of that space, some of that pressure is being taken up by water vapor as we humidify the air. Here, we're also giving the partial pressure of carbon dioxide. We didn't calculate it on the previous slide because it's very small, but we do have carbon dioxide in the lungs. And as we start to think about gas exchange, we're going to be paying attention to that carbon dioxide as well. These are not yet numbers that you need to remember. We are going to want to remember the partial pressures of oxygen and carbon dioxide once we get to thinking about exchange with the blood, but we don't need to know exactly what they are in the atmosphere, just hear that they're changing as we humidify the air. That's the key takeaway for this. So the other thing we need to pay attention to, other than the pressure of gas, which is kind of an indirect measure of its amount because of that percentage piece, so we need to take into account the fact that different gases are going to have an easier time dissolving into a liquid. So they have different solubility. And this depends on both the properties of a specific gas and a specific liquid. For our purposes, because blood is mostly water, we really think about how soluble our gases, specifically oxygen and carbon dioxide, are in water. So that's an approximate measure of how soluble they are in blood. So what we're going to be thinking about, right? I'm going to draw. So this is our alveolus, right? So this is where our air is originally. And then we have our capillary running by. We know there's a lot of vasculature running through the lungs, right? So we're thinking about oxygen and CO2 in both of these places. So I'm just going to look at our oxygen. Now we can express a partial pressure in a gas, but we can also express a partial pressure in a liquid. Okay. So this also has a partial pressure. 2. And when we're thinking about the respiratory system and we're thinking about this gas exchange, these pressures are going to work the way other pressures and gradients work throughout anatomy and physiology, which is to say they're going to come to equilibrium. So as we have gas exchange happening, we're going to have the partial pressure of the gas coming to equilibrium with the partial pressure of that gas in the blood. But because of this solubility issue, it's going to be slightly different in terms of the amount. Okay. And that'll hopefully make sense as I continue to talk. But we're knowing here that we can have a pressure in the air, we have a pressure in the blood, and they come to equilibrium as they sit here and undergo gas exchange. So the solubility of a gas and a liquid is subject to something called Henry's law. And all this says is that there's a relationship between the concentration of our dissolved gas, its pressure. So these are those partial pressures we've been talking about, and a constant. The other thing to know here is that there are going to be different constants for different gases. So there's like a different constant here for oxygen and a different constant for CO2 that expresses something about the solubility of those gases in our substance. Okay. So here's why we've been talking about this. So oxygen and CO2 have really different solubility in water. So at 100 millimeters of partial pressure, so we're saying at a partial pressure of O2 of 100, okay, 0.15 millimoles of oxygen get into a liter of water. If we're at a partial pressure for CO2 of 100, and when we give a partial pressure, we want to be specific about what gas we're talking about. So for the second line, we're not talking about the partial pressure of oxygen anymore. We're talking about the partial pressure of CO2. So when our carbon dioxide is at that same partial pressure, if we had that same amount of carbon dioxide in the air, we'd get 3 whole millimoles of carbon dioxide into that same liter of blood. So we don't have very much carbon dioxide in the air around us, right? It was only 0.03% of our atmosphere. But because it has a really easy time getting into the blood because it's so soluble in water, this is why we're going to have amounts of oxygen and carbon dioxide in the blood that are on like the same order of magnitude, basically, because of this huge difference in their solubility. So here we see an example of what we're talking about this partial pressure of oxygen in the gas versus in water, and how that relates to the solubility. And we're going to compare this to carbon dioxide. Okay. So in this first bit, what we're comparing, right, is we're saying we have a partial pressure of oxygen of 100 in the air when we start out, right? So we're counting up those air molecules, and that pressure is related to what the percentage of oxygen is in the atmosphere, or we could calculate it using our ideal gas laws if we knew the volume of the container, the temperature, and the number of moles of oxygen. But we're starting out at a partial pressure of 100 for oxygen in the air. And down here in this figure, our partial pressure of oxygen in the water is 0. So we're saying there's no dissolved oxygen in this water at the start of this experiment. Now, like all sorts of gradients, right, we want to move towards equilibrium. That's just a physical property of the universe, right? We're going to come to equilibrium. So our partial pressures are going to try to equalize so that the partial pressure of oxygen in the air comes to the same partial pressure in the water. So to do that, to get that partial pressure of 100 of oxygen in the water, all we have to do here is move, in this picture example, one of these molecules of oxygen into the water. Realistically, the concentration comparison would be we'd have 5.2 millimoles of oxygen in the air versus 0.1 millimoles of oxygen in the water, but these both express 100 millimeters of pressure in their respective environments. So when we compare this to the solubility of carbon dioxide, so we're running the same little experiment thing, but we're looking at a different gas. So if we had a partial pressure of 100 of carbon dioxide now, we're also starting with a partial pressure of carbon dioxide of 0. They're still going to come to equilibrium. But this time, we're not just moving one little bubble into the water, we're moving 2, because carbon dioxide is more soluble in water than oxygen was. So we could also compare our actual measurements of moles. So here we see that same 5.2 millimoles of carbon dioxide in the air. But we see that to get that same partial pressure of carbon dioxide in the water, it took a whole 3 millimoles. So we have to put more carbon dioxide into the water in order to get that same partial pressure. So now we're going to start thinking about how these partial pressures are affecting our alveoli and our blood. So gas exchange is happening at a couple of different places. So the one that's probably at the top of our minds now is the gas exchange that's happening in the lungs, right? So the carbon dioxide and oxygen crossing those type 1 alveolar cells, the basement membrane, and the capillary endothelium. The other place we have gas exchange happening is in respiring tissue. So in the tissue that is metabolically active, right? So it's soaking up oxygen so that it can do cellular respiration, and it's giving off carbon dioxide. right? So that's another place we have gas exchange happening, right? As it's sucking up that oxygen and putting out CO2. And both of these things are going to affect the partial pressures of oxygen and carbon dioxide in our blood. We're also going to see that we're going to have to pay attention to the partial pressures of each of these in our alveoli in that air, and we're going to have to take into account this gas exchange happening. So, like everything else, gases diffuse down gradients. When we're thinking about our gases, we're thinking about pressure gradients here. So they're going to move from areas of high pressure to areas of low pressure. So even though we're still talking about, even though now we're talking about these partial pressures, the same basic rule that we've seen throughout this course is going to apply, moving from high pressure to low pressure. So that applies to our whole mixed gas, but it also applies to a partial pressure. So any particular gas is going to diffuse down its own partial pressure gradient. So the oxygen doesn't really care about what the partial pressure of the carbon dioxide is. It's going to diffuse down the oxygen gradient. The carbon dioxide is going to diffuse down the carbon dioxide gradient. So we're going to be paying attention to the partial pressure of each of these gases, and they're going to be pretty much independent of each other, at least in terms of the gas exchange happening. Okay. So here's where we're going to be focusing our time. So we're going to start up at the lungs, I think. So we've seen the beginning in our atmosphere. We started with a partial pressure of oxygen at 160 and a teeny tiny pressure of carbon dioxide happens to be 0.3. So that's out in the air around us, the air we're breathing. As we move through the conducting zone, we humidify that air, we change its temperature, which drops it down. Those numbers aren't here on this graph. What we have instead are the exact partial pressures of these gases in the alveoli. So this is after we take into account that fresh air and dead air mixing, basically. So numbers you do want to remember here, because they're going to be very relevant for our partial pressures in the blood. The partial pressure of oxygen in alveolar air is 100 millimeters of mercury. Our partial pressure of carbon dioxide is 40. Right. So we're way higher for carbon dioxide than we were out in the atmosphere. We're a bit lower for oxygen. So that's in our alveolar air, which means that as blood circulates through those pulmonary capillaries, so surrounding the alveoli, these are the partial pressures we're going to come to equilibrium with, right? So the capillaries surrounding the alveoli are going to exchange gas until they also have a partial pressure of oxygen of 100 and a partial pressure of carbon dioxide at 40. I'm going to start using different colors here. So a thing to note about this figure is just to remember that our lungs are the one place where we're going to see our arteries and veins colored the opposite colors than they usually are. This is because pulmonary arteries bring deoxygenated blood to the lungs, because an artery just means it's defined as something moving away from the heart. So our pulmonary veins are actually these red ones because they're moving back to the heart. So this is the freshly oxygenated blood in those pulmonary veins that's coming to 100 for oxygen and 40 for carbon dioxide. So this means that in our systemic arteries, as we pump that blood, right, that blood from the lungs, goes into the left atrium, then the left ventricle, then out through the aorta and out into our systemic circulation. In our systemic arteries, we're going to see those same concentrations of oxygen, or sorry, those same partial pressures, I should say, of oxygen and carbon dioxide. So oxygen is going to stay at 100, carbon dioxide is going to stay at 40. So this continues on until we get to the capillaries around our respiring tissue. So we have in yellow our tissue. Right, so our tissue here is using ATP, so it's making ATP. So it's doing cellular respiration, which is our internal respiration. Then we start our external respiration as we have this gas exchange happening with the blood. So it is exactly replacing the amount of carbon dioxide and oxygen that we were exchanging in the lungs. So as we see here in the tissue, we see a drop in oxygen. Right, so here's our drop in oxygen because that oxygen is getting soaked up into tissue. So this is still telling you basically that we're coming to equilibrium with this amount of oxygen. So because our cells are using oxygen, they don't have a partial pressure of 100 because they're constantly using it. They're at 40. Carbon dioxide concentration here in the tissue is 46, which means that our blood is coming to equilibrium with these partial pressures of the respiring tissue. So as we return blood from these systemic capillaries around the tissue into our cardiovascular system, we're going to see that they have matching partial pressures because they came to equilibrium now with that tissue. So now that we've passed the tissue, our partial pressure of oxygen has dropped down to 40 to match the tissue. So it went from 100 in the systemic arteries to 40 in the systemic veins. And we've also picked up some carbon dioxide along the way, right? So our systemic arteries had a partial pressure for carbon dioxide of 40, but they grabbed some carbon dioxide from the tissue. They came to equilibrium with the carbon dioxide in the tissue. So they're now at 46. So 100 partial pressure of oxygen in arteries, 40 partial pressure of oxygen in veins. 40 is also our partial pressure of carbon dioxide in the arteries. 46 is our pressure of carbon dioxide in veins. As we have the blood circulate back to the heart, right? This deoxygenated blood is not actually fully deoxygenated, right? Like our blood doesn't go to 0 in terms of deoxygenation, it just drops down to 40. So that's our deoxygenated blood with a partial pressure of oxygen at 40 circulating back to the heart and then circulating along into the lungs. So if we're very specifically thinking about a pulmonary artery, right? So pulmonary artery, still deoxygenated. So we're still at a partial pressure of oxygen of 40, right? Because we haven't gained any oxygen yet, because we haven't passed an alveolus. Still at a partial pressure of carbon dioxide of 46, right? No gas exchange has happened here, still in the pulmonary arteries. Not until we get all the way back to our lungs, to the alveoli, that we get rid of these additional 6 carbon dioxide and we pick up 60 more oxygen as we come to equilibrium with the air in the alveoli. So this is this whole cycle here, and these numbers you do want to be familiar with. So we want to know what our partial pressures should be in a systemic artery versus a systemic vein, a pulmonary artery versus a pulmonary vein, and in that gas exchange happening with the alveoli. We can pay attention to those differences, and we can realize that we are replacing basically the oxygen that's getting used here in the tissue is getting replaced by oxygen we're breathing in. So this is why we can have a consistent amount of oxygen in our arteries, because as we use it, we suck it back up from the alveoli. The same thing is happening with the carbon dioxide. Carbon dioxide that we're putting into the circulation here, into the veins from the tissue, is getting released into the alveoli and breathed out as we expire, as we push air out of our lungs. So we're going to stop here for today. Bit of a chunky concept, and we'll pick up here on Wednesday. It's today, Monday.